Hi, this is Kan-Lin薛from National United University Department of Energy Engineering. And in the material and energy balance around fuel cell, in the previous section we talked about the test station and then the flow rate of the hydrogen as well as the air we able to calculate based on the Faraday's law and for a fuel cell stack. And then, the flow rate also had to account not only theoretical consideration, also had to consider the stoichiometric ratio and the operation mode. Is a dead end mode, recirculation or purging mode? All this had to be considered. From there, we keep going and calculate the fuel cell composition. If a fuel is not pure, then how we can handle that. And in this section, we are talking about air humidity. It's one important factor for the low temperature fuel cell, such as proton exchange membrane fuel cell, direct messenger fuel cell, even the phosphoric acid fuel cell, because in the water will be carried in from the airstream. It can be humidify the fuel cell like a PEM fuel cell. But also sometimes it had to be low humidity in order to carry out the excess water generated by the fuel cell. So air humidity control is very important for the lower temperature fuel cell. What air humidity, that actually you can find from the website. There's a lot of textbook talk about it. Oh, here just brief introduce those kind of things. First, the humidity can become divided into the absolute humidity and the relative humidity. In the absolute humidity, there's two the ratio. The one is the molar, based on molar ratio, humidity, the mass ratio, and the molar ratio. The mass ratio is X, is a mass of water vapor divided by mass of dry air. The humidity based on the molar ratio, Xi, is equal to mole of the water vapor divided by mole of dry air. Actually, in the air, since there's water in there, so it's a wet air. But the most definition we use the dry air because the dry air during the humidification process, the dry air molar number of mole of the dry air or the kilogram of the dry air do not change during the humidification process. The dry air do not change, but the total wet air mass or the molar ratio mole will be changed. So in the calculation, use dry air will be easier because it keeps constant during the humidification process. So this X and Xi can be interchanged, can be converted each other easily. For the X, actually is a mass of water vapor divided by mass of dry air. If this we times the molar weight of the dry air and the water, then we end up with the X times MA divided by NW, the water molar rate. So this one divide this, and actually we can coming out equal to the molar of water divided by molar of dry air, actually equal to Xi. So this one you can convert from X times the molecular weight ratio of air and water, we can get a molar humidity ratio, Xi. And vice versa, we can from the Xi times molecular weight ratio, we can get the mass humidity ratio X. Next, we can think about the partial pressure. Since all this air coming in, even the water is in a vapor form, is air, we can assume is an ideal gas. can be used PV equal to nRT to represent, because molar ratio you can use a mass flow rate to mass flow control meter to monitor and control the flow rate, and also the pressure is a way of monitor that. The molar flow rate of the water is equal to the pressure of water vapor times the gas volume divided by R and T. And then the dry air, the molar is equal to the pressure of air, PA, times the gas volume, and divided by R and T. The R is the universal constant, and T is the temperature in Kelvin. So the gas volume is maybe you can consider as a molar volume, but it doesn't matter because over here you will cancel out for a given volume. So over here the Xi equal to the molar of water divided by molar of dry air, and we substitute those PV divided by RT. Then over here for the water and then dry air, the V over RT cancel out each other. So the Xi equal to PV divided by PA, the partial pressure of vapor divided by partial pressure of dry air. And then the total pressure of the air side equal to the vapor partial pressure plus the vapor pressure of the dry air. So the PA equal to P minus PV. We can substitute this PA into the Xi equation. We end up with so as long as we know the vapor pressure, we're able to calculate the Xi, the molar humidity. The previous is X and Xi is the absolute humidity based on the actual molar ratio of the water and the dry air. Now we talk about the other index is a relative humidity. The relative humidity is a PV divided by PVS. The PVS is the vapor pressure at the same temperature is the saturated vapor pressure. And then the PV is the partial pressure is at the same temperature but it's not saturated. Actually the partial pressure in the air. So the PV equal to 5 times the PVS. So from here we had 3 different humidity definition. X is a molar, is the mass humidity mass ratio, humidity based on mass ratio, and the Xi is a humidity based on molar ratio, and then the phi is a relative humidity based on partial pressure, the saturated vapor pressure of water, and then they can inter-exchanged from the phi to Xi or the phi to X, and the X Xi also can be exchanged. You can see from the above equation. Now over here, the PVS is a saturated water vapor, saturated pressure of water, and this one from the 0 degree to 100 Celsius can be calculated. In the literature, you can find out this one or other different similar equation. And over here, you can see this the number. In this one only good for pressure at 1 atmosphere. And then this saturated water vapor pressure over here. You substitute those numbers, you can calculate the vapor pressure at a different temperature from 0 to 100. Above that, maybe has slight deviation. There's also had a steam table. You can find out at a different temperature pressure. The steam table is very useful. You can find out from the literature. Equation over here just easy if you use Excel spreadsheet computer programming. You can use this equation, it's much easier. Now next we can see the enthalpy of air at a given humidity and the temperature. For the dry air, at a given temperature T, the entropy is Hg, is a specific heat of the air, the Cpg, times the temperature. The reference temperature you can give any, but over here apparently give the temperature is 0. Is maybe any reference temperature over here, but they will cancel each other. And then the water vapor. Water vapor, you had the temperature times the water vapor specific heat of water vapor, the Cpv, and plus the HFG. The HFG is entropy, the latent heat. That means the water evaporation, heat of evaporation, or the latent heat of the water vapor and then the liquid water. The evaporate from liquid water to vapor, how much energy required. So for an air contain X amount of water, then the entropy HVG equal to the dry air entropy plus the water entropy. You can get the wet air entropy. But sometimes the water had a water droplet, so the amount of water droplet is XW. So the water droplet, the entropy of water is a specific heat of water Cpw times the temperature, give it the water entropy HW. So for an air, you had the water vapor and the water droplet, like a fog in the air in the morning. Then the entropy can be calculated by this equation. The first item is the dry air. The second is the water vapor. The third is the water droplet entropy. You can count everything here. Now we use the diagram. We call this a Mollier diagram. This diagram is a plot of the humidity air, the entropy of humidity air, joule per gram, plot against the water content, the gram of water per gram of dry air. On the open space, over here is the unsaturated region, and then on the brown region is the fog region. That means inside contain the water and the vapor mixed region. And then the borderline is the saturation line, where the relative humidity equal to 1. And then in the unsaturated region, there's different relative humidity line. This line I just plotted arbitrary, just a schematic present those is not accurate. It's better you find the real Mollier diagram, then you can give it a much accurate curve. So for instance, if I had the air at the point A, where the entropy, something like that, and then with the relative humidity is 0.4. So if I cool down the air, remove the heat from the air, the entropy of the air will be reduced gradually to a point to the saturation line, the B over here. Then after if at this borderline, if you keep reduce the air temperature, then it will precipitate the water out from the air. And this one you can call the B is the dew point. The temperature at the B will be the dew point. And to the C, then it will end with in the fog region where the air maybe contains some water droplet inside. For another example, if from the D relative humidity is 0.2, then I keep adding water. This may be adiabatic process or heating, non-adiabatic process, doesn't matter. If you keep adding water, they will be moved from in this diagram to the right hand side, and then will touch the saturation line. If you keep adding the water vapor, then will keep will be precipitated into the fog region F. So next, we're going to look at how it happens if the humidification process taking place at a constant temperature. And this is a saturation line. And this equation for enthalpy of air at a different amount of water content and the temperature. So if at a constant temperature, this is a constant temperature line. If you operate at humidification at a constant temperature, then the point will be moving along with the constant temperature line curve. This is because over here, this equation, the XV and XW is a water amount inside the air. And then the C, if we keep it at a constant temperature, T equal to constant temperature, then all the other items will be constant. So the enthalpy of the air equal to C1 plus C2 HXV plus C3 XW. Because all this C1, C2, C3 is a constant, we can lump together maybe to C4 is a function of temperature and X. So we move along a straight line over here if T is a constant here. And what happens will be if we add the humidification process at the adiabatic process, there's been no heat added in or removed. So from this similar diagram, the enthalpy will be kept at a constant. So there will be the constant enthalpy line. If you add the water at the adiabatic process, will be follow the constant enthalpy line. And for the pan fuel cell, you can see on the test station in the back usually had a water tank on the hydrogen side and the air side. The dry and the cold air will be bubbled through the water tank with a given temperature, maybe 60 Celsius degree or 80 Celsius degree. And the dry cold air, the humidity may be X1, temperature at the T1 at the lower humidity and the lower temperature. After it goes through this, bubbles through this water tank, it comes with wet, warm air with a humidity XS and a temperature raised to T2. From this Mollier diagram, there's a constant enthalpy line and then constant temperature line and then the relative humidity line. We can plot all together. This humidification process may be from, say, at a humidity, relative humidity 0.2, and then the temperature at the T3 over here, and then will be goes through the adiabatic process along with the constant enthalpy line H3 and then move to the saturation line, or maybe to the XS T2 and the phi 2 over here.